Hello. We're going to begin our study of inviscid flows, which are flows where viscosity is not important, by talking about static flows. Hydrostatics is the study of fluids that only have normal stresses. That means there's no shear stress. And no shear stress means that the velocity gradient is zero from Newton's law of viscosity. So if the velocity gradient is zero, and we have a no-slip boundary condition where the velocity at the wall has to be zero, that means the fluid everywhere is not moving, hence the term hydrostatics. Now, in terms of what kinds of equations we're going to use to analyze these systems, we're going to start with our conservation of mass and the Navier-Stokes equation. So, starting with conservation of mass, since we have a static fluid, we can cancel all the terms that have velocities in because they're zero. And we end up with this that the density does not change over time, which basically means that all static fluids can be considered incompressible. The next equation that we're going to look at is momentum, which is the Navier-Stokes equation. And again, we're going to cancel all the terms that include velocities, because the velocities are zero. And once we simplify, we end up with this equation, which is just the balance of body forces and pressure forces. Here the gradient of pressure is the net force by pressure per unit volume, and rho g is the body force per unit volume. So we can rewrite this as the equation of hydrostatics, which tells us that the pressure on a fluid is basically equal to the weight of the fluid above it that it must hold up. Now, we can expand this out and analyze it in a little bit more detail. We can break this down into the three coordinate directions, x, y, and z. And if gravity is in the negative z direction, then we can see that there's no pressure change in the x or y direction, just in the z direction. And because there's a negative sign, it means that as you go down through the fluid, the pressure is going to go up, which makes sense. Then we can integrate that equation with respect to the z-coordinate to get the total change in pressure between 2 points. Now, gravity is constant for most of our engineering calculations, so we can remove that from the integral and treat it as a constant. And if a fluid is truly incompressible, liquid water for instance, where density is not a function of pressure or is a very weak function of pressure, we can take density out of the integral and this equation becomes very easy to solve. If we have a compressible flow like a gas, for instance air, density depends on pressure. So as you go up through the atmosphere, the density of the air decreases. And in that case, you have to integrate correctly. You have to get density as a function of pressure, and then you're integrating pressure with respect to z. So you have to do a little bit more complex integration. Now, it's often convenient to use what we call the free surface as the reference pressure. So this symbol here is going to denote the free surface, which is where the fluid, the liquid, interfaces with the air above it. Now, the pressure at the free surface is typically something like atmospheric pressure. For instance, the surface of water in a large tank would be at atmospheric pressure. Now, to make this problem easier, we want to change our coordinates. We want to go from the height, z, from the bottom of the tank, to the depth of the water, or whatever other liquid is in this tank, h. So we want to convert from z to h, from height to depth. So we convert, and then we get a new equation that pressure change is equal to rho gh, or pressure is surface pressure, P0, plus rho gh. So in this case, we can see that the pressure depends only on the depth from the surface, not on the shape or size of the container. It also tells us that we're going to need to pay careful attention to our coordinate systems in this unit, because we're going to be using coordinate transformations to simplify problems throughout the next few presentations, videos. Now, we can also divide this equation through by rho g, and then we have pressure over rho g and height. So every term in this equation is going to have units of meters, or dimensions of length. This quantity, P over rho g, is called the pressure head, and it's often used in industry to characterize pumps and compressors and stuff. Basically, it's the height of a column of fluid that would be held up by that much pressure. I also want to show you this simulation. This is from the University of Colorado. And we go to this web page, and it's got this. You click on this. It's a Java applet that you can run. I've already done that, and you can see we can look at the pressure at different locations. We can move these sensors around. We can change the fluid density. We can change gravity, and we can see how this changes. So we're going to add some water here, and we'll just flip this, fill it up, and here we have atmospheric pressure. We have the pressure at a couple of different points, and you can look at changing the density, and you can look at changing gravity and see how that affects pressure. You can also look at, this is the depth in meters. You turn off the atmosphere so there's no atmospheric pressure, and you can play around with all of these different behaviors. You can also look at this one where you can actually look at the pressure at different points at the same height, and you can see that again, pressure is only dependent on depth, not the shape or size of the container. There's also an interesting presentation here where you can add some weights over here that changes the behavior. So you can see adding weight. We'll talk a little bit more about this when we talk about hydraulic systems. So the next question we should ask ourselves, we're talking a lot about pressure in this module, so it makes a lot of sense to ask what exactly is pressure. Now this is a little bit of a review from our initial module. The technical definition is the normal force per unit area. Now pressure is caused by the vibrating molecules that collide with the surface of an object or with other molecules in the gas. And there's another simulation that demonstrates this concept very well. If you follow the link, you can see there's this gas properties, and we can add gas molecules. We can change the size of the container to increase the temperature and pressure. Here we can turn up gravity. Oop. These are heavy molecules, so if we turn up gravity, we can see the change in density as a function of height, where it's very dense near the bottom and less dense near the top. And you can add heat and remove heat and play around with how we can observe pressure. Now, Pascal's law says that the pressure acting on a point in a fluid is the same in all directions. There's some important implications for this. It means that if we increase the pressure at any point, it'll cause the same pressure increase everywhere else. And this idea is important for hydraulic machinery, like hydraulic lifts and so on. Most of the time, we actually describe pressure as a gradient. In the Navier-Stokes equation, we have the gradient of pressure. So we typically need to have some reference pressure to give us a boundary condition. Now, the first of these is absolute pressure, which is pressure relative to a vacuum, for instance, the vacuum of space. The other one is gauge pressure, where we measure the pressure relative to the atmosphere. Now, this is convenient for measuring since we don't need to carry around a vacuum chamber. So, for instance, a tire pressure gauge measures the gauge pressure inside your tire. So if your pressure gauge shows a pressure of 10 psi in your bicycle tire, we know that the local atmospheric pressure is 14.7 psi absolute, so then the absolute pressure in the tire would be 24.7 psi. Now, standard atmosphere is a good reference state for our problems. The pressure is 101.3 kilopascals, and the temperature is 15 degrees Celsius. Gauge pressure is going to change depending on the condition of the atmosphere. So if you have a system with the same absolute pressure of 200 kilopascals, but you measure it on 2 different days, you might get different gauge pressures because the atmospheric pressure has actually changed. So there's some interesting behaviors there. We can also look at pressure measurement devices like a barometer, which is used to measure atmospheric pressure. It's basically a tube of liquid turned upside down, and at the top of the fluid there's a vacuum or a very low pressure vapor. So the pressure in that vacuum is equal to the vapor pressure of the fluid. As an example, the vapor pressure of mercury is about 1.6 times 10 to the negative 6th atmospheres at room temperature. And atmospheric pressure then is about 760 millimeters of mercury. So atmospheric pressure will hold up a 760 millimeter height column of mercury. It'll hold up about 10.3 meters of water. We also have U-tube manometers where you compare the pressure in two different systems. Typically P1 would be something like atmospheric pressure. It'd be open to the atmosphere. And then P2 would be something that we're trying to measure the pressure of. And so we can measure the height difference on the two sides and use that in the equation of hydrostatics to come up with the pressure. We can also use inclined tube manometers. Now, these are used to measure very small pressure differences. It's easier to get accurate measurement because the length, the distance you're measuring, is increased due to the angle. It's also important to note here that we have this datum line. The datum line represents the level of the fluid if the pressure in the reservoir and the tube are the same. When we pressurize that reservoir using some system, fluid actually leaves it. And so the height of fluid in the reservoir drops. So the actual height difference between the two sides is actually higher than the difference between the datum line and the tube height. So we need to account for that when we solve problems using this type of manometer.